So the next type of machine that we will learn of is called as a linear bounded automata, right? So again, to give you the context here, right? So linear bounded automata is related to context sensitive languages, right? And context sensitive languages are generated by context sensitive grammars. If you recall, we have studied context sensitive grammars when we learned about the Chomsky hierarchy of grammars and languages, right? So I'll recap some of that here, and I'll also explain you about the automata here, right? So just to give you some context here, what is a context sensitive grammar? Again, it's a recap of what we already learned, right? So a context sensitive language has production rules like this, where the length of the LHS should be less than equal to the length of the RHS. Or in other words, this RHS should be greater than equal to the LHS. And both these LHS and RHS, they cannot contain epsilon, right? Or in other words, they are strings that belong to V plus T positive closure, right? So you cannot have epsilon on the right side. This is what we have seen as the definition of context sensitive grammars when we learned about the Chomsky hierarchy, right? And context sensitive grammars generate context sensitive languages. And the machines that accept context sensitive languages are called as linear bounded automata. Now let's understand the linear bounded automata and connect the dots of a linear bounded automata to the context sensitive grammar. I'll argue that both of them are basically, so CSG is generating a context sensitive language which the linear bounded automata is accepting. I'll do it in a very intuitive way. So first and foremost, your linear bounded automata is nothing but, okay, so let me write it down, right? So it is basically an NTM. It's a non-deterministic Turing machine. And in addition to non-deterministic Turing machine, it has a bounded tape. It has a bounded tape. I'll explain you what is a bounded tape. And it's a linear bounded tape. It's a linear bounded tape. So I'll explain you what each of these pieces means. We know what is a non-deterministic Turing machine. We know everything about a Turing machine. By bounded tape, what I mean here is, this is your input tape. In a typical NTM, remember, the difference between NTM and a DTM is, in NTM, on the same input symbol, you can have multiple transitions, right? So it's a bounded tape because unlike a typical Turing machine, we don't have infinite tape on both sides. We have special symbols typically. We have the special symbols typically written as a dollar symbol and a C with a cross, right? So these two are called the special symbols. And I can only use, right, my linear bounded automata. So I can write my linear bounded automata as a non-deterministic Turing machine with a bounded tape. To bound the tape on both sides, I have my two symbols, right? This is called the left end marker. This is called the left end marker. This is called the right end marker. These are two special symbols, right? So they signify the bounding of the tape in the sense that my header cannot move beyond this or beyond this. My header has to move only within this region. My header cannot move to the left of it. My header cannot move to the right of it, right? Except that this is a read-write tape. Just like in your Turing machine, this is a read-write tape, right? So this is a read-write tape, just like in your Turing machine, but it's a bounded tape. And the length of this tape, what should be the length between the left and the right end? That's also an important question, right? So imagine if you're given an input word W, right? The binding or the limitation on the length should be linear in terms of W. That's what it means, right? So it should be linear in terms of the input word. That's why the name itself, linear bounded automata. It's an automata where I have a tape which is bounded and the bounds itself are linear, which means imagine if the length of the word is, let's say, W, right? If the length of the word is W, what does linear bounding basically mean? It means the length of the tape from the left end to the right end should be a linear function of W. What are linear functions? Linear functions, we can write them as A length of W plus B. This is a linear function, right? This is a linear function. What is a quadratic function? Quadratic functions can be written as this, right? So these are quadratic functions. This is a quadratic function in W, or in the size of W. This is a linear function. That's what I mean. So this is called a linear bounded automata because this length is linear in the length of the input word that you're passing to your LBA. Okay, these are the three aspects of it. Now, if you want to think about it mathematically, right, you have your set of states. Look at this. You have your set of states. You have your input alphabet. You have your tape alphabet, just like your Turing machine here, right? So you have your blank symbol. Wherever you don't have an input word, you will have blank symbols, right? Because this length can be more than your input word. So your input word may be from here to here. Let's say your input word is from here to here. Rest everything should be blanks. Just that this whole length has to be linear for some constant A and B. Here A and B are constants here, right? So you have blanks here, very important. Then you have your left marker, you have your right marker. These are special symbols, right? Then you have your initial state, you have your final state, just like the finite control part of a Turing machine. What about this? What about this part here? What about this part here? This part here, you have your initial state Q. Look at this. This is the state that I am currently in. This is my input symbol. We said it's a non-deterministic Turing machine here. So this means given a current state and a symbol, I can go to a set of states. I can write them with a set of symbols that I have and left or right. Right? This is exactly the transition function of an NTM. Right? So if you look at it mathematically, it has 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 9 tuple. Right? So if you think about it, it's a 9 tuple. The only special thing here is this. The only special thing here is the left end symbol, right end symbol, and your header cannot cross them. That's very important. Your header cannot go to the left of this. Your header cannot go to the right of it. That's very, very important. Right? So this is what is called as a linear bounded automata. So when we learned about the Chomsky hierarchy of grammars and languages, we said that a context sensitive grammar does not contain, so a context sensitive language does not contain epsilon, right? So whatever the context sensitive grammar generates, it cannot generate epsilon. So there is no epsilon in a context sensitive language. But there is a small problem here. I can design my linear bounded automata by making the initial state as the final state. Imagine if I make my initial state as final state, right? And if I don't define any other transitions, what happens then? Well, initially I'll start the initial state. Look at this. I'll start in the initial state. I don't define any other transitions from there, which means given any symbol that comes now, right, it will always halt, right? So given, I'll also make this as my final state. I'll make my initial state as my final state, right? Now, if I get epsilon as an input, what happens now? If I get epsilon as an input, because my initial state is a final state, my LBA is accepting it. But here I'm saying that LBA and context sensitive grammars are one and the same. And now there is a contradiction here, right? See, an LBA can accept, we can design an LBA that accepts epsilon, right? But we are saying here that context sensitive grammars will never generate epsilon. Isn't there a contradiction here? There is. So the equivalence of an LBA and a context sensitive grammar is true only when you ignore these epsilons. Right? Because I can always generate an LBA that accepts epsilon by making the initial state as my final state. Right? Obviously, because look at this mathematical construction here. I can do that, right? So LBAs can accept epsilons, but context sensitive grammars can never generate epsilons. This is a contradiction. To get out of this contradiction, we say that an LBA is equivalent, right? An LBA is equivalent to a context sensitive grammar in the sense that this accepts context sensitive languages. This generate context sensitive languages as long as the languages are epsilon free. Okay. So again, look at this. This generates context sensitive language. This accepts context sensitive language. As long as it is epsilon free, this equivalence holds. This is a very, very important boundary case that many people forget to address. Okay. Forget to appreciate also, right? This is a very, very important boundary case here. Now, if you think about it, if you think about these grammars and languages and machines, right? So let's look at this, right? So you have your regular languages, right? On top of it, you have your context-free languages, right? On top of it, you have your context sensitive languages. On top of this, you have your context sensitive languages. On top of this, you have your recursive languages. On top of this, you have your recursively enumerable languages. Right? Look at this hierarchy. This is your Chomsky's hierarchy, right? Now, similarly, if you start writing this down, you have finite automata. On top of it, you have your deterministic PDA. Right? Look at this finite automata, whether it's deterministic or non-deterministic, they're equivalent. Then you have your deterministic PDA. Corresponding to your on top of your deterministic PDA, you have your non-deterministic PDA, which we just call PDA. Then you have your LBA. Look at this. Then you have your LBA. On top of your LBA is your Turing machine. Look at this. On top of your LBA is your Turing machine. So here, if I have to write this context-free language can be broken down further into two parts, right? There is deterministic context-free language. So let me break this down for you. Okay. Just to be clear here. So let me break this down further, right? So this circle here is deterministic context-free language. This outer circle here is the regular context-free language, which can be generated by non-deterministic PDA or PDA in general, right? So this is what you have. Similarly, you have grammars also. You have regular grammar, deterministic context-free grammar, context-sensitive grammar, right? And for this, you have your unrestricted grammars here corresponding to these. Or to be more precise, your unrestricted grammar is corresponding to this. Your unrestricted grammar actually corresponds to recursively enumerable languages, to be more precise, right? So this is your hierarchy of languages, hierarchy of grammars, and hierarchy of machines, right? Very, very important. So if you want some examples, okay, of context sensitive languages, let's look at some examples, right? Suppose imagine if I have a language like this, a power n, b power n, c power n, such that n is greater than equal to 1. This is obviously a context sensitive language, right? I can actually write a linear bounded automata. Again, why is it a linear bounded automata? Because my input length is 3n. Now I can just limit my tape as a linear function of 3n and still do it. Remember, when we built a Turing machine for this, we did not use the full Turing machine itself. By which I mean we did not need the whole infinite tape itself, right? So if my whole input was here, right, let's say AA, BB, CC was here, I just needed few more elements here, and I just needed few more elements here that I was using, right? So for this language, this was perfectly all right. So I can actually construct a LBA also to accept this language, because I didn't need the whole infiniteness on the left side and the infiniteness on the right side when I was constructing a Turing machine for this, right? I just needed to use a few more here, that's it, nothing else, if you recollect this, right? So what's happening here? So which means I can construct an LBA for this, which means this language is a context sensitive language. Now let me change this slightly and make it not context sensitive. Imagine if my language is like this, a power n, b power n, c power n, such that n is greater than equal to 0. Now what is happening here? This language now, if n equals to 0, there is epsilon in this language. There is epsilon a, b, b, c, c, all of this. Now the moment you see epsilon, you can say this is not a context sensitive language. Even though you can construct a linear bounded automata for this, this is not a context sensitive language, because by definition, context sensitive languages should not contain epsilon, right? So it's very easy to see. Again, remember, if you want to determine whether a language is context sensitive or not, the easiest way to think about it is there a grammar which satisfies these rules? Can you construct a grammar that satisfies these rules? Or can you construct a linear bounded automata where you cannot use the infiniteness on this side and this side, and whatever length you are using here should be linear in terms of whatever input you are given. That's all there is, right? So again, these are all nice examples of, again, this is a very nice example to show a language which is CSL, and by just changing it slightly, it's no more a CSL, right? Very, very interesting. Now, just like all other languages, we can come up with closure properties also, right? So if you look at closure properties of context sensitive languages, there is one property under which it is not closed. Obviously, clean closure. Look at this. If L is a context sensitive language, then what is L clean closure? L clean closure will consist of epsilon, right? The moment you have epsilon, this is not a context sensitive language, right? So it's very obvious to understand that for context sensitive languages, they are not closed under clean closure, but they are closed under positive closure. Look at this, they're closed under positive closure, because if you think about it, positive closures are one or more concatenations, right? And we have seen for the concatenation operation, look at this, just like the way we have seen for a Turing machine, we can also construct the same concept for a linear bounded automata. The only thing we have to care about when we're designing a linear bounded automata as compared to a Turing machine is I can't keep using infinite tape, and whatever additional tape I'm using has to be a linear function of whatever I have here. That's all I have to care about. That's all, right? So it can do concatenation, which means it can do positive closure is allowed, union, intersection, reversal, substitution. Look at this, epsilon free homomorphism. As long as your homomorphism does not contain epsilon, this is called as epsilon free homomorphism. Similarly, inverse homomorphism and intersection with regular languages. Under all these operations, your CSLs are closed. Your context sensitive languages are closed under all these operations. Again, we can easily arrive at some of these things just the way we have done it for Turing machines. I've shown you some intuitive proofs of how these closure properties are derived or how these closure properties are justified for Turing machines. Similar arguments we can do it for LBA also very easily. The only thing we have to care about is the space used is a linear function of inputs, and I can't just use the infinite tape. That's all. Rest everything stays the same as far as LBAs and Turing machines are concerned. But remember that under clean closure it is not closed because clean closure introduces epsilon. That's all. Again, the concept of LBAs is very, very similar to the concept of Turing machines, except for this bounding or linear bounding part. And this linear bounding part is not a huge hamper to you. It doesn't hamper your theorems or proofs dramatically. And also please remember that LBAs and context sensitive grammars are equivalent as long as we ignore epsilons. This is a very, very important boundary case that we have to be aware of.